Hello, let's talk about disjoint set data structures, also known as union find. A disjoint set data structure is used to keep track of a set of elements partitioned among disjoint non-overlapping sets. So this kind of algorithm is used in Kruskal's algorithm for finding the minimum spanning tree of a graph. Also, it is used to detect cycles in a graph. Also, there are some constraints for using union find. One is that it only works in undirected graphs. Also, there should be no self-loops in the graph for this to work. We discussed that it can be used to detect cycles in a graph. Let's see how. So let's say you are given a bunch of edges of a graph, and then we can manually connect these edges and form a graph. So 0 is connected to 1, 1 is connected to 2, 1 is connected to 3, so on and so forth. Then you notice that there is a loop or a cycle in the graph. We can visually see it. But how can you tell a computer to find out if there exists a loop or a cycle in a graph? In other words, how can a computer tell that if it connected all these edges, it would form a loop or a cycle? This is where union find comes in. So the algorithm works by creating a bunch of sets in the beginning and then iterating over all the edges and then finding the set in which both the vertices lie. If they lie in the same set, then there is a cycle in the graph. If not, then we merge both those sets and then move on to the next edge. Now, when we merge the two sets, then we are going to create or assign a root of that set. It can be either the first vertex or the second vertex. It's up to you. Which one do you choose? But you have to be consistent. So now when you assign this root, this is also called as the parent of the set or the root of the set or the representative of the set. Either of these three things will work. So let's call it root for our test case. So the algorithm in short looks like this. In the beginning, we make V number of sets. V is the number of vertices. In here we have 5 nodes or 5 vertices. So we will make 5 sets. And then in the beginning, we will put one node in one set individually. So there will be one node in one set. Then I told you earlier that we need to create a root or a parent or a representative of a set. Now in the beginning, when there is only one element in the set, so we make it its own root or parent or representative. Alright. And then what we do is we iterate over all the edges and find the root or the parent for each vertex, like the set in which they lie. And then we see if the root is same or if the parent of both these sets is same, that means there is a cycle in the graph. If not, then we merge those two sets. That is also called unionizing of two sets. So let's run this test case against this algorithm and see how it works. So in the beginning, as I mentioned, we are going to create V number of sets. Here there are 5 nodes, 5 vertices, so we'll create 5 sets. So we will have 0, 1, 2, 3, 4. And these are the sets, and each set contains only one element. And we told that in the beginning we are going to make it every node as its own parent or its own root. So let's say this line represents the roots. So 0 is its own root, 1 is its own root, 2 is its own root, so on and so forth. Now let's iterate over the edges. So the first edge is 0, 1. So the first vertex is 0. We find which set it lies in. 0 lies in vertex, in set 0. And what is its parent? 0 itself. Then what is 1's parent? 1 lies in this set and its parent is 1 itself. Are they same? No. Then what do? We unionize them. What unionizing does is now this set does not point to itself as its parent, but it points to 1 as its parent. So now this set is gone. Now this 0 has a root 1. So 1 is 0's root. So if I ask you to check what is 0's root or a parent or representative, then you should say 1 because now it points to 1. We merge the two sets. Now you could have made 0 as 1's parent. It doesn't matter. You have to be consistent. In here, I'm making the second vertex as the parent of the first. Or you can make it vice versa, but be consistent. So, okay, we finished first edge. Then let's go over the second edge. Second edge has two vertices, 1 and 2. We find what is 1's parent. Well, 1's parent is 1 itself. as we know already, and 2's parent is 2 itself. Then are they same? No. Then what do? We unionize them. So now 1 points to 2 and 0 was already pointing to 2. Alright, so let's move on to the next edge, 1 and 3. We find what is 1's parent? Well, 1's parent is 2. What is 3's parent? 3's parent is 3 itself. So is 2 equal to 3? No. That means we unionize them. So now 2 points here, 1 was already pointing to 2, 0 was already pointing to 1. So this set is no longer existent as it in itself. Alright, let's move on to the next edge, 1, 4. What is 1's root? 1's root is 2, 2's root 3. So 1's root recursively is 3. What is 4's root? 4 is 4 itself. So are they same? Is 3 equal to 4? No. So what we do is now 3 points to 4. So we merge them, and that means 3 now points to 4. So now if I asked you what is 1's parent, it is recursively 4. So, okay, now let's move on to the next edge. 2, 3. So what is 2's parent? 2's parent is recursively 4. What is 3's parent? 3's parent is also 4. Are they same? Yes, they are same. What does that mean? That means there exists a cycle in a graph. Yes, of course there exists a cycle. When we go over 2, 3, yes, 2, 3 does makes a cycle. So that's how union find works. In the beginning, we create V number of sets, V equal to the number of vertices in the graph. Then we make each node as its own parent in the beginning. And then we iterate over all the edges and find the parent of both the vertices and see if those parents are same. That means both the vertices lies in the same set. That means there is a cycle in the graph. If they are not in the same set, we merge them and then move on to the next edge. This is how union find works. Thank you.